Hello everyone and welcome. In today's demo, we'll walk through on how we can streamline model debugging and solver integration using the Run Solver tool. Ensuring model integrity and consistency is a critical part of any simulation workflow. In cases where multiple model setup iterations are required, efficient debugging tools are essential. Run Solver tool is designed to simplify this process by offering instant job submission, execution, monitoring, and interactive issue detection. We have prepared two practical cases where the capabilities of the tool will be showcased. In the first one, typical model integrity issues will be observed and tackled during a static analysis of a car's tailgate using the Applicis solver. We access Run Solver tool through Durability Ribbon tab. Solver Group, Durability, Solve, in or out of ANSA. Before executing an analysis, let's first switch to the Options tab to review the tool settings. The first field, which is the only mandatory, should point to the solver executable. We switch back to the Analysis tab. After having set a path for the output file, we can start the solution. An error message pops up. Hovering over the message file, we can see a fatal error related to a specific material that is being used by a property. By just using the hyperlink, we can access the material. By entering its card, moving to the Miscellaneous tab, we can see that the material is undefined. So we switch the defined field to yes. Press OK, and then let's proceed with the second attempt to execute the analysis. We repeat the same process to output and submit a new output file. Another error indication appears. Let's find out what is the error in this case. As we can see, the fatal error is related to an RB3 element that induces singularity during the solution. Again, via using the hyperlink, we can detect the desired RB3 entity. Opening its card, we can examine its settings, where we notice that there is a mismatch between the DOFs of the dependent and independent nodes. This is the cause of the singularity. We can resolve this by constraining additional DOFs on the independent nodes. Click OK, and we move on to the third attempt. We execute the third analysis. The solution stops with another error indication. It is clear that the fatal error is related to a poor element quality issue. More specifically, the element with ID 122 violates mesh quality criterion. Let's find out more details by focusing on this element via isolating it. Let's bring the neighboring elements visible. It seems that the solution error is being caused by this needle element. Let's fix its quality by using a local mesh improving algorithm. The Brush tool can help us to do so. We can access it through Surface, Mesh Ribbon tab, Edit Mesh. Press B key button and reconstruct the area. As we can see, the violating element has been deleted. Let's go back to Solver Run tool and try a fourth attempt for a successful solution. It seems that we have managed to solve it successfully. Let's continue with the next practical case. Moving on to the second part, we will handle the contact inconsistency errors arising during a static analysis scenario of a car braking mechanism while utilizing the Abaqus solver. This time we'll use the load logs function in the Run Solver tool to review solution attempts. The model was pre-solved to save time, and all attempts were logged. This lets us explore the generated files and demonstrate how errors were identified and resolved. By pressing the Browse icon, we can access the first attempt file. Press Load. The files generated during solution are available in corresponding tabs. Moving to the Dot tab, we can search for the error. The error indicates that contact inclusions keyword is required for the proper definition of a general contact. Above the error line, we can see the definition of contact initialization assignment keyword that is used only for general contact definitions. Accessing the contact list, and by activating the type of contacts, we can see that we don't have any general contact definition here. It seems that the contact initialization related keywords have been defined here accidentally, so we can just delete them in order to resolve the error. Moving to the second attempt, let's load the related log or DAT file. We see 47 errors. The goal is to resolve them sequentially and observe how the solution evolves. Using the arrows, we locate the first error. It indicates that there is a missing parameter, tabular or value. Scrolling up, we find the clearance keyword used in a contact definition without being followed by a value. Let's access the contact pair list and sort them by those using the clearance parameter. We notice that all have values except contact ID 33. The blank value likely caused the error. Right-clicking and updating the clearance value resolved it. Let's move on to the next attempt and check the outcome. We load the files generated during third solution attempt. In the same manner as previously, we are searching for the first error. The message mentions that when the same combination of contact surfaces definitions is being used both by a tight contact and a contact pair, causes solver error. In order to resolve this, we need to delete one of those contact definitions. Using the hyperlink of the highlighted surfaces, we access the contact pair that uses them. Let's delete it. Let's move on to the fourth attempt. Finally, there is no error message. We have managed to complete the solution successfully. Let's now explore additional capabilities of the Run Solver tool. The first feature focuses on reviewing the model's contacts by retrieving the relevant data from the ODB results file. Typing info in the search bar to find the info message related to the contact status. By clicking right mouse, Contact Status, show ODB file scanning is taking place via using Meta in the background. Let's isolate some parts of the breaking mechanism so that we can easily see the contact status on the surfaces. Also, let's disable the visibility of the contacts for the same purpose. Now we can clearly view the slipping and sticking contact areas with blue and red color respectively. We can also select the result state from which we want to retrieve the contact status. Finally, another capability of the tool is that it reads sets created by the Abacus solver and stored in the ODB file. By typing outside in the search bar and clicking the warning message, we see details about nodes missing intersections or lying outside the adjusted zone. Abacus generates node sets when contact nodes fail to project onto the main surface or fall outside the adjust zone. A highlighted hyperlink appears. Clicking it retrieves the node set from the ODB file, making those nodes available in our database for further handling. Thank you all for watching this video.